Okay, so we are going to start today's lesson with a review of our last lesson. We did learn about the first derivative test and the second derivative test and concavity up to this point. Can someone just unmute themselves and confirm that you can see and hear me? You can see my lesson?
Oh, we can, Miss.
Thank you. Okay, so first question is asking us to find intervals of concavity as well as the coordinates of any points of inflection. So right away, because I know that concavity and points of inflection are related to my second derivative test, I'm going to take the original function and go straight to calculating my second derivative. Well, first of all, I need to take this cubic function and apply the power rule in order to get a quadratic function as my first derivative. And from the quadratic function, I know I'm going to get a simple linear function for the second derivative. So just like I showed you in our last class, we take this function and set it equal to 0. And once we have the function equal to 0, I can solve for x, just like so, taking x minus 12 and setting that equal to 0. Now, very important that if I'm going to use x is equal to 12 to find possible points of inflection, not guaranteed point, but possible points of inflection, it really requires me to take x is equal to 12 and substitute it back into the original function, not the first derivative, not the second derivative, but the original function. So I'm going to take my x is equal to 12 and plug it in to my original function, so 1/3 times 12 cubed minus 12 squared plus 5. So that gives me still a possible point of inflection. On the test, you really cannot state that something is a point of inflection unless you have proven this with our sign table. Now, just some reminders from last time that when the second derivative is equal to 0, we have an undefined or possible point of inflection. However, in the sign table, when the second derivative is less than 0, a negative number, that proves that the original function is concave down. And when it's greater than 0, f of x would be concave up. That's what we've really learned up till now. So if I take my possible point of inflection, and we always have the negative infinity and the positive infinity on the outsides, and that gives us 2 intervals in our table, and I'm choosing test values that are close to the possible inflection points. So when we plug these values into the second derivative, I'm going to get positive 11 and a negative value, and I plug in 11 into the second derivative, I will get a negative value. And when I plug in positive 13 into the second derivative, I will get a positive value. That is what I need in order to prove that my original function, not the second derivative or the first derivative, but the original function is concave down. And when the original function is concave up, that's because my second derivative is greater than 0. Now, because it is possible to move from concave down to still moving concave down, or from concave up to concave up. But in this case, because there's a change in direction, that proves that the point of inflection is in fact x is equal to 12 and y is equal to negative 1,147. So I can write my final answer as concave up between the interval of 12 and positive infinity, and concave down from negative infinity to positive 12. So the great thing about Module 3, the reason why we place it in the course, usually in the regular Mary Ward course right before optimization and after derivatives is not because just because it uses derivative rules, but also because it provides a nice breather. It's a kind of a nice simple unit that where the steps are very straightforward, very few exceptions to any rule, and it is known to be one of the easier tests when you compare all 18 units in the Mary Ward course. Okay, so at this point, I'm really going to draw into our knowledge of MHF and MCR to give you some reminders about rational functions. I think that's very important since there are some students that are taking MHF at the very same time this quadmester as calculus. So whenever our degree of the denominator, remember there's a full unit dedicated to this in the latter part of the MCR course. And we learned then that when the degree of the denominator is greater than the degree of the numerator, that indicates that we have a horizontal asymptote at y is equal to 0. So there's no value there, just when y is equal to 0. That's my horizontal asymptote. At the same time, we can find vertical asymptotes from the zeros of the denominator or the restrictions in the denominator. So if I set x minus 2 equal to 0, I can solve that x cannot be equal to positive 2. So that means there's a vertical asymptote at positive 2. If x squared minus 4 cannot be equal to 0 as per the rule of rational functions, that means I can factor x squared minus 4 to x plus 2 and x minus 2. And that means that we have 2 vertical asymptotes. Now remember, whenever you have vertical asymptotes or multiple critical points, that makes you the sign of your table, your sign table, your first derivative test or second derivative test table a little bit more complicated, where you don't just have one critical point. So we're going to look at some examples of that. And of course, when x minus 1 squared cannot be equal to 0, that means that you will have a vertical asymptote at x cannot be equal to positive 1. So x is equal to 1 would be our vertical asymptote there. So this is a slide. Remember, we were very lenient when we're marking the module 1 and 2 study notes because we introduced this concept a little bit later in the course. But now as you prepare for your module 3 and module 4 tests, we really want your study notes to be detailed when it comes to the important things to remember from the lessons. The next scenario is quite a simple one. It's when the degree of the denominator is equal to the degree of the numerator. At this point, the vertical asymptote is still the 0 of the denominator. So because I have x minus 1 in the denominator, I can expect a vertical asymptote at x is equal to positive 1. But here we're going to really discuss the horizontal asymptote. We have to take the quotient of the leading coefficient. So remember, in this example, we have a 3x in the numerator and an x to the power of 1 in the denominator. Now, x to the power of 1 is the same. The degree of the denominator and the numerator are the same. So what we are going to do is look at the leading coefficients. Positive 3 divided by positive 1. Well, 3 divided by 1 is going to give me y is equal to 3, and y is equal to 3 gives me a horizontal line at y is equal to 3. So that is the equation of our horizontal asymptote. And finally, a situation that we haven't really looked at and is more a concept that you're going to explore fully in university as opposed to your high school course is when the degree of the denominator is less than the degree of the numerator. In this case, we have an oblique asymptote, which is also the quotient of the numerator and the denominator with a vertical asymptote at the denominator. So we might come across this in very few examples in your unit work. So I have included this in our notes for that reason. Now that we've discussed some vertical and horizontal asymptotes, let's reach back and clarify the difference between a vertical asymptote versus a hole in the graph. And I'm actually going to touch upon a concept we learned in Module 1 with limits. Okay, so usually you are never given an equation when it's fully factored. You're expected to do that. But in this particular case, we know from the factoring that there will be a vertical asymptote at x is equal to +1 and x is equal to positive, so x cannot be equal to +1. And at +2, there's something different that's going on. So let me highlight the vertical asymptote at x is equal to +1, because x minus 1, if we set that equal to 0, we know that x is equal to 1, as well as the fact if we try to plug in 1 into our equation, we are going to get an undefined 0 in the denominator. So that does indicate there's a vertical asymptote. However, at x is equal to +2, you'll notice that x minus 2 and x minus 2 are both in the numerator and the denominator, so they have to cancel. If we try to plug in +2 into our equation, we would get an indeterminate. We mentioned that in Module 1, situation where you have 0 in the numerator and 0 in the denominator. That indicates that when x is equal to +2 and y is equal to 1, we will definitely have a hole in the graph. But you notice the 0 over 0 is different from the undefined value we got when we plugged in the vertical asymptote, x is equal to +1 into the equation. So this is a removable discontinuity, and it is clear that from Module 1, we learned that even though this is not a continuous function, the graph still has a limit because it's approaching at x is equal to 2, the same value from the left to the right. So we can conclude that if you're plugging in a certain x value into the function and you get a number over 0, in this case, that value of x is a vertical asymptote. However, when you're plugging in an x value and you get 0 or over 0, an indeterminate, that indicates that there is a hole in the graph. Now, often, a math course is like connect the dots. We really want to reach back and connect the concepts we're learning now with the different modules. So we will be talking a little bit about limits, although limits are not going to be on the Module 3 test. I do want to reach back a little bit and connect the dots. So I'm just going to exit the screen a little bit, and there we go. Go back to full screen mode. Okay, so we do want to review the limit definition of asymptotes. When you have a vertical asymptote, your limit is approaching positive infinity and negative infinity. However, when you have a horizontal asymptote, you're approaching one particular value of your limit, and horizontal asymptotes only exist if the degree of the numerator is less than or equal to the degree of the denominator. That we covered in the rule, in the previous rule. So let's do some examples of actual equations where we're just solving for the horizontal asymptote. So if you're given an equation like this, the first thing you want to figure out is, first of all, the leading terms. And the leading terms, we have an x squared and another x squared here. So we have exactly the same degree in the numerator and the denominator of the leading coefficients. So we would take, or the leading terms. So we would take the leading coefficients, which are 3/6, and we would reduce that. So our horizontal asymptote happens when y is equal to 1/2, because 3/6 simplifies to 1/2. Okay, but what happens if you have an equation where the leading terms are not the same? So in this particular question, we have 3x squared in the numerator, but an x cubed in the denominator. So this is when you go back to your other rules. For this particular case, because the numerator, the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is automatically y is equal to 0, the x-axis. Now, we use the first derivative and the second derivative in order to come up with crucial points to curve sketching. So, sorry, one more example. When we have a situation where the numerator is simply 1, and our denominators are a very clear algebraic expression. In this case, it's factored. We have clear asymptotes at our restrictions, and our horizontal asymptote is also equal to 0 because the degree of the numerator is less than the degree of the denominator. Now, as I was saying before, our first derivative test and second derivative test gives us, the advantage of that is that it gives us components of the graph, such as points of inflection, concavity, increasing and decreasing intervals, and maximum and minimum. Now, even there's a reason why we do curve sketching with first derivatives and second derivatives and not limits, although limits still tell us the behavior of the graph and what direction it's moving towards. It doesn't give us any concrete facts other than that. So if I wanted to connect this particular graph and kind of get an idea without using first derivative or second derivative of the behavior of the graph, I would take these two vertical asymptotes, x is equal to -2 and x is equal to +3, and I would perform double-sided limits on that. Remember, you're not going to be expected to do this on the test, but if we use a test value close to -2 on the as we're approaching from the left, so approaching -2 from the left, I would see that the graph moves towards positive infinity. If I'm approaching -2 from the right, the graph is moving towards negative infinity. And if I'm approaching the other asymptote from the left, I'm going to move from negative infinity to the right, which is positive infinity. So I'm just including this to show you how limits could be possibly applied to curve sketching. And if we actually plug this function into Desmos, you will see that the different components, so to the left of -2, to the right of -2, the asymptote at -2, to the left of the vertical asymptote at x is equal to 3, and to the right of the vertical asymptote at x is equal to 3, does match the information that we discovered using limits. However, the first derivative and second derivative test gives us some much more useful information, and that is why we rely on those concepts heavily for curve sketching. Now let's consider this function, a very simple quadratic function where the degree of the denominator is greater than the degree of the numerator. So right away we know the horizontal asymptote is y is equal to 0. This is one of the most popular horizontal asymptotes that you will see in many different graphs because the degree of the numerator is often less than the degree of the denominator. For the vertical asymptote, however, we cannot factor this, and you will see if you graph this that there are no vertical asymptotes for this particular equation. So we do possibly have a continuous graph. Now, if the question is asking you for local max and min points or intervals of increase and decrease, we know that for this particular section, I'm going to focus on the first derivative and the first derivative test. So you'll notice 1 over x squared plus 1, even though it's a very simple function, it still requires us to use the quotient rule. So plugging that in, the quotient rule, you'll notice because there's a constant in the numerator, I do have a derivative of 0 for the numerator, which makes this easy to simplify. You have to have a simplified version of the first derivative. Once we do that, we find critical numbers by setting the first derivative. We're going to set the first derivative equal to 0. And when we do that, set the first derivative equal to 0, you'll notice that the denominator, when we cross multiply, the denominator times 0 is equal to 0. It effectively eliminates the denominator. So I have a value of x is equal to 0. So that's my x value of my critical point. In order to get the y value of the critical point, I have to substitute not back into the first derivative, but into the original function. So to find a clear critical point, I do need to figure out the value of f of 0, not f prime of 0, but f of 0. So that gives me a critical point of 0, 1. So this particular function only has one critical point according to the first derivative test. So I would take that critical point, 0, 1. I have a negative infinity on the left-hand side, a positive infinity on the right-hand side, and only 2 test intervals, so 2 test numbers. When I plug those test numbers into the first derivative equation, you're going to figure out that the positive first derivative indicates that between negative infinity and 0, my function has an original function has an increasing interval, and between 0 and positive infinity, it will be decreasing. And that proves that the point 0, 1, the critical point that we found, is going to be a local maximum because we're moving from an increasing interval to a decreasing interval. And the way that your textbook would write that is like this: from negative infinity to 0 would be an increasing interval, and from 0 to positive infinity would be our decreasing intervals. So that is the first derivative test. Now, the same equation, same function, I already know the first derivative, but in order to find possible points of inflection, the first derivative is no use to me. I have to take the second derivative, and this is going to require a more complex calculation because we still have a quadratic function that is going to require the chain rule in the denominator. And I have to take the second derivative by applying both the chain rule and the quadratic function. This is the whole reason we had that topic for our last test. Now, you would get partial marks for plugging in the product rule and quotient rule and chain rule properly. But for some students on the test, they jumped from that step. all the way to the final answer. And that's not how you earn full marks in math. You really have to show your progression, show your steps. So simplify this section to get something like, oops, to that, but to get something like that, to undo that step. There we go, and back to full screen mode. And after that, you want to apply your distributive property. If you're going to take the greatest common factor out, that's fine, but you still have to simplify the leftovers. In this case, we simply have to apply the distributive property twice. So I should be able to look at your final answer and look at especially the two steps that come before that, and be able to solve in my head. If there's a lot of distributive property that's left and I can't see the progression from one step to your final answer, that's where students lose marks. So please be careful about that. Now, in order to find possible points of inflection, and I keep highlighting the words possible, not definite. This is a possible point of inflection. We set our second derivative equal to 0. Notice by doing this, the 0 cross multiplies with the denominator and effectively eliminates the denominator, but we still have this x squared when we're simplifying. And it's very important to realize, unless you're dealing with real life applications where negative values cannot be or do not make sense, you need to consider the positive and negative situation. So this time for our possible points of inflection, we have two possible points of inflection, a positive 0.577 and negative 0.577. You will find when you plug both into the original function, you're going to get the same y value, but there's still two different x values. So our sign table, our second derivative test table, is going to look a little bit different, because now we, instead of just 3 intervals, we have 4 possible intervals and 3 possible test numbers in each interval. So this time I'm plugging each test number into the second derivative equation. I don't need to know the values. Remember, I just need to know the sign of the second derivative. Positive sign, so when the second derivative is greater than 0, that indicates that the graph is concave up. Now, it's possible in the sign table to go from concave up to concave up and concave down to concave down. But in those cases, we would not have a point of inflection. Because we're moving from concave up to concave down and then back to concave up, that proves that both of the possible points of inflection are in fact inflection points. So all we need to prove that is this sign table to confirm that we're moving from concave up to concave down. That's not the same as proving local mins and max. And finally, we can use Desmos as a tool to plug the equation into the graph to understand that this is a continuous function. The first derivative did confirm that we have a local maximum at 0, 1, and 2 points of inflection. So that's really all we were asked to do for this particular question. So we have now summarized effectively the first derivative test and the second derivative test. I have included a table here, which kind of really clarifies what you can tell from a function from the original graph, the first derivative, and then the second derivative. So you'll notice the first derivative test, we're talking about maximums and minimums and rising and falling, increasing and decreasing intervals, whereas the second derivative test, we're it still kind of indicates what maximum and minimums or can clarify, prove further things about maximum and minimums. But more importantly, is in the second derivative test is inflection points and concavity. And I've also included, so this should be really in your study notes. And the last part that I've included is just some general rules, a general approach to curve sketching that I want you to read through, and you can come up with your own step 1, step 2, step 3 to figure out what to do in curve sketching as we go through a few more lessons, and especially when we get to optimization. I am going to give you in language a step-by-step process of really what methods and rules you should be following in your as you prepare for your test. So